Welcome to this workshop. This is the sixth session, and the topic I'm going to cover today is a bit complicated. So, I'm going to cover a unit impulse function. Okay, I'm just going to give a simplified treatment of this. Okay, and for a rigorous treatment of this, so you can refer to the textbook that I had mentioned in the first session. So that is Signals and Systems by Oppenheim and Wilsky. Okay, so a unit impulse function, the definition is bit complicated. So it exists only at a point. Okay, so this delta of t is equal to 0 for the argument not equal to 0. Right, it exists only at t equal to 0, and it is such that so the area under the impulse or the total area, right, is equal to 1. Okay, so this is when you integrate a function, so you're basically finding the area under the curve, right? So area under the curve is basically equal to 1. So this is the definition, right? So it's a bit more complicated than your unit sample sequence, the counterpart of the discrete time case, right? Now here, so you just need to know a little bit of discontinuous functions, the term meaning of the term continuity. Okay, so this is from calculus. So suppose I have a function something like this. Okay, so I have a function. Okay, so let this value be equal to, so I have a time axis here. So this is my time axis. Okay, and let this value be equal to 5, and let this value be equal to 6, and this value of time, let's call it as t1, is equal to let's say 10 units. Okay, whatever it is, so whatever the unit of time may be, right? So let's say x of t1 equal to 10, right? So there is a discontinuity. So what do you mean by the term discontinuity? So discontinuity means, so what I'm going to do is, so I'm going to approach t equal to t1, the point t equal to t1, right, from the left hand side. So I'm going to move along the curve, right? Okay, and I'm going to approach the point t equal to 10. Okay, so I'm not going to write t1 again, so since I have defined it as an instant, so at t equal to 10th unit, right, so the minus on top implies you are approaching the function, the point t equal to 10 along the function, okay, from the left hand side. So when you approach this point, the value of the function that you are approaching is equal to 5. Okay, because so you can see the curve. Okay, as you come from left hand side, so the value of the function takes is equal to 5. Okay, so this point, right? So minus indicates you are approaching the point t equal to 10 from the left hand side. Okay, so this is called as the left hand limit, or in short LHL. Okay, and what I'm going to do is, I'm going to approach the point t equal to 10 from the right hand side. Okay, and I see that I am approaching the value when I move along the function, right, in this direction. Okay, so this is how I moved to find out the left hand limit, and this is how I am moving the direction to find the right hand limit. So as I approach the point t equal to 10 along the function, right, along this path, the darkening path, right, so I am approaching the value of 6. Okay, so this is called as the right hand limit of the function at point t equal to 10. Okay, so in short RHL. Okay, so this function where the right hand limit is not equal to the left hand limit, right? So this function is called as a discontinuous function. Basically the function has a discontinuity at a specific point. At all the other points it is continuous, right? So you can take some random point. So let's say this is value 1 at t equal to 0. This is the point at t equal to 0, the function value let it be equal to 1. Okay, so if you approach from right hand side, so you are approaching the value of 1. So if you approach from left hand side, you are approaching the value of 1. So it is continuous at t equal to 0. Whereas if you approach the function at t equal to 10, right, so it has two different values when you approach from left hand side as well as when you approach from right hand side. So the function is said to be having a discontinuity at t equal to 10. Okay. And now what happens is when you try to find out the slope at discontinuities, okay, so what you get is, so the slope will be infinity. Okay, so mathematically the slope at discontinuities is infinity. As you can see, it's a vertical line, so there can be no slope greater than a vertical line. Okay, so the slope is the highest, so which is equal to infinity. Okay, now so either you can use the definition where x of t plus delta t minus x of t divided by t plus delta t minus this one t limit delta t tending to 0. At this point t equal to 10, you will get the slope to be equal to infinity, right? So the denominator goes to 0, whereas the numerator will be equal to 6 minus 5 1. Okay, so the slope will be infinity. Right? So now what to do? So what physicians did is they defined a function, right? So when you try to calculate a slope, okay, so again as I am telling you, the rigorous treatment of this is given in this textbook. Okay, so you can go through that. Okay, so the at discontinuities, right? So if you take a derivative of the function, right, so there will be some function called as a Dirac delta function, right? So this function, a unit impulse function, is sometimes called as a Dirac delta function, right? So suppose if I have a function which is called as a unit step function, so again you will come across this frequently in the textbook. Okay, and you can see that, so it's one of the test signals that is employed to test a system. So this is when you encounter the time domain analysis in a control system course. Okay, so one of the test signals that is fed to the system is a unit step function, and you will be studying the response of a unit step function to the system. So the definition is as follows: a u of t is equal to 1 for t greater than 0, and it is equal to 0 for t less than 0. Now what is the value of function at t equal to 0? The value of the function at t equal to 0, right, is not defined. It has a discontinuity at t equal to 0. So when you draw it, so it looks something like this. Okay, so it is 0 here when t less than 0, and when t greater than 0 it is 1, and at t equal to 0, right, so have the value equal to at t equal to 0 the value is undefined, right? So there is no particular value at t equal to 0. So we basically say that there is a discontinuity at t equal to 0. Right, so this is a unit step function because it has a step here at t equal to 0, right? And when you take a derivative of this, so mathematically at t equal to 0, if you calculate the value, so you'll get infinity, right? But since we have defined the new function, so the slope of this will be equal to delta t. Okay, Now, why is this unit impulse function so important? Okay, so as in the discrete time case, as we defined a general signal or a general sequence in terms of time shifted impulses, so we can do the same, right, in the continuous time case. Okay, so it's very difficult to cram in the definition and then explain how x of t is formed by the time shifted impulses. So if you are interested, you can mail me, so I'll explain it. Okay, so where tau is the running variable. Okay, so a dummy variable or a running variable. Okay, so the rigorous treatment is given in the textbook. Okay, so if you don't understand, so you can mail me, so I'll try to explain it. It's very difficult to explain in the 15-minute time limit. Okay, so what I did here was, so x of tau is a number. Okay, and again delta t minus 2 is a shifted impulse. So I am expressing a general signal, a general function as your integration is nothing but shifting and adding, right? So you are shifting it by the amount delta tau and then multiplying two functions and then adding them up. Okay, so again in some sense you are taking a linear combination, okay, of scaled time shifted impulses. Okay, so that's about it. So there is a one-to-one relation here, right? Any general discrete sequence can be expressed as a linear combination of scaled time shifted unit sample functions, and the same thing goes for the continuous time functions. Okay, so let's stop here and we'll continue from here in the next session.